so far we talked about was like an introduction to finite state machines. To explain what we mean by finite state machines and the design process of a finite state machine, and we finished with a simple example. We will do more examples today for binary and modulo and counter, which are basically finite state machines as well. And this will help you as well to design any type of finite state machines in future. So that is, I think you know what we mean by a binary counter. So it counts, and the modulo n counters is they count as well, but not necessarily they follow the normal counting sequence 0, 1, 2, 3, and then it doesn't necessarily go to the, if we say 2-bit, it doesn't mean it will have all possible states, which are 0, 0, 0, 1, 1, 0, 1, 1, and counts. So this is the difference between the normal binary counters and the modulo n counter. So modulo n, this means they have n valid states. So we can say, for example, we count from 0 to 3, not from 0, sorry, from 0 to 2, not from 0 to 3. So 3 is not a state, a valid state. So I have, in this case, I will call it a modulo 3 counter. So it has 3 valid states. So this is the main difference between them. So we'll talk, and of course, as I said, it doesn't necessarily count up, so it can count down. So we have different, you can design whatever you want. Once you know the concept, you know the design process, you should be able to design whatever you want with different states. Right, so we'll start with the binary counters, and then I will move to the modulo and counters. And for binary counters, we have 2 types. We have synchronous and asynchronous. We already talked about this, synchronous and asynchronous. So if we say we have a preset, for example, if we say this is asynchronous, this means it doesn't depend on the clock. And if we say it's synchronous, this means it depends on the clock. So it's controlled by the clock. We wait for the clock first, and then we check the preset. So again, it's related to the clock. The same here, when we say this is a synchronous counter, now we are talking about the counter, the whole counter. We are not talking about specific inputs. So we say this counter is asynchronous. Again, it's related to the clock. Again, counters consist of flip-flops, D flip-flops or JK flip-flops. And all flip-flops, they require a clock. Now, if all the clocks, all the flip-flops, they have the same clock, so which means if I have another flip-flop here, and they all have the same clock, in this case, we say that this is synchronous counter. All flip-flops are controlled by the same clock. But if it is not the case, so if this flip-flop is not, the clock for this one comes, let's say, do you remember the example that we gave you in the tutorial? So the clock comes from Q bar, for example, or comes from Q. Then the clock for this flip-flop is not the same as for the first one. So they don't have flip-flops in the circuit. They are not controlled by the same clock. In this case, we say it is asynchronous. And we have, when we design them, it's the process is different. And then I will give you examples for each one. Right, so I think I talked about this. I explained it, what we mean by synchronous and asynchronous. Of course, as I said, if the counters, for all cases, we use flip-flops, JK or D flip-flops. Yeah, and as I said, the difference between the two is the way the counters are clocked, or the flip-flops inside the counter are clocked. So this is the main difference. Right, we will start with asynchronous binary counter. So as I said, for asynchronous binary counter, the clock for, if I have 3 flip-flops, so these are the clocks. So we will have the main clock here, we start with it, and then the next flip-flops are not clocked with the same clock. So we take it from the previous one. So in this case, we say it is asynchronous. And it's easy to design this type of circuit, of this counters. But the disadvantage of this circuit or this counter is it just counts up. So it gives you 0, 1, 2, 3, 4, and so on, and then back. This is how it works. So it counts up, it increments by 1 every clock cycle. So the design is very simple. You just take flip-flops and you clock them this way. You know, the same circuit that I showed you in the previous tutorial. I mean, we gave you the circuit, and when we draw the waveforms, we found out that it's a counter, right? We did it, and then so this was the circuit, if you remember, using JK flip-flops. I can do the same using the flip-flops. So this is exactly the same circuit that we did. So as you can see, this is the first clock, and then we take those are the next clock. So if I want a fourth one, if I want a fourth bit, so this is 3-bit counter. So this counts from 0 to 8, to 7, sorry. Now if I want a fourth one, it's very simple. I will just add another flip-flop here, and this will be Q3, Q3 bar, and then we will have the clock, and the clock comes from here. And that's it. It's all what I need to do. And then, of course, the J and K will be 1. It's always a toggle operation. We did this in the, and we showed you that you will get a counter, counting. If I want a fifth one, I will just do the same. I will just follow it this way. So it's a clear how we build this circuit. And again, the disadvantage, as you can see, it's simple. We need only flip-flops. We don't need anything else. And we can increase the number of flip-flops, or you can increase the number of bits in our counter. The same I can do it with the D flip-flop by connecting the D's to, is connected to Q bar of the previous one. And then the goes here. D goes here. If I want a fourth one, I will just have the clock. So the clock comes here, and then this goes here, D, Q bar, and this is the Q, and this will give me another bit, and so on. So I can add to this. This is basically the solution that we did in the tutorial, right? So when you draw the waveforms, so to get, this is Q0, this is Q1, and this is Q2. I'm not going to repeat it, so it's a toggle operation. And then, of course, we take them all as the final output, which will be here 3 bits. This is the final output. I think we did this in tutorial, so there is no need to repeat it. And then that's it. This is for asynchronous counter. If I want to use the flip-flop, I can use this circuit. If I want to use JK flip-flops, I can use this circuit. And again, do you remember this is the clock divider. So we have clock dividers basically connected together, and then this will form a counter as well. Right. Now, the second type of counters is the synchronous counter, where all flip-flops will be, or will have, the same clock. So if this is the clock, then all of them will have the clock. If I do this, and if I take J and K, for example, sorry, JK, and I will have 1 here, this will not give me a counter. 1, 1, Q, 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 Q bar, Q bar, Q bar. So if I do this, I will not get a counter, and you can try it. So there is a need to add extra component here. which we call the excitation logic. In this case, this is a pure finite state machine, and we need to identify even the previous one is a finite state machine. But the process of designing it is different. Now, this is a finite state machine, a pure finite state machine. We need to find out what should we do for J and K to get what we want. For each flip-flop, I need to find out what should be J and K to get what we want. Right, so we need an excitation logic. And this is the disadvantage of having this circuit. So we need of using synchronous is there is a need of extra component. But again, the advantage is you can implement whatever you want, whatever sequence you want. So it's not necessarily just counting up. We can count up, we can count down, you can mix, you can have different types of sequences, you can increment by 2, you can increment by 3, you can do whatever you want. Right. So this is what I'm going to show you next. And you will see that in this case, this is like it will be the internal structure of the counter. So we need, we will get it from the excitation table. This is combinatorial. And this is flip-flops. And those will be connected this way. So I will show you the process, the whole process, how to design this, which is very similar to the one of a finite state machine. So the first thing to know is to know how many flip-flops you need. So in this example, I already mentioned here 2-bit synchronous counter. What I want to do, we already showed you how to do asynchronous. So if I want 2 bits, this is 2 bits. 2 flip-flops together, we'll connect them this way. Now, what if I want to do it synchronous? So which means I will need 2 flip-flops and they have the same clock. But what should I do on J and K? This is the question for each one. Or what should I do for D flip-flop? I will do the example with D. We will do with the JK later in the tutorial. So if I want to use D flip-flops. Now, the first step is to know how many flip-flops you need. But since here I already mentioned 2-bit, then we know that we need 2 flip-flops. So each flip-flop will give us 1 bit of the output. Or if we don't know this information, let's say that I gave you in the question, I say I want a counter that counts. We know that, so the number of flip-flops, so the maximum value is 3, which is equal to 2 power m minus 1. 2 power m minus 1 is the maximum number. If I have 2 bits, I can go up to 3, right? Which is 2 power 2 minus 1. If I have 3 bits, I can go to 2 power 3 minus 1, which is 7, and so on. So in general case, 2 power m, I think I put it here. Oh, yes, I didn't mention it. So general case, 2 power m minus 1, where m is the number of flip-flops that we need, or the number of bits of the output. Again, the number of flip-flops is equal to the number of bits in the output. But if we tell you in the question, we tell you 2-bit synchronous counter, it's clear. 2 bits, it's 2 bits, we need 2 flip-flops. But if I say, okay, we want a counter that counts up to 7, then you, of course, 2 power m minus 1 is equal 7, and then you get the m, and so on. And then we said each flip-flop will give us 1 bit. So the next step, you assign which for each flip-flop. So for example, the first flip-flop, if I call it flip-flop 0, I will have Q0 from it. I will have D0, Q0, Q0 bar. And then I will have flip-flop 1. Usually we start from 0, right? When we talk about the number of bit 0, bit 1. So if we say flip-flop 0, so we get the Q0. The Q0 will represent the first bit of the output, the least significant bit. So we will have Q0, Q1, 0, 0, 0, 1, 1, 0, 1, 1. So Q0 is the first flip-flop will give me the first bit, and the second flip-flop will give me the second bit, and so on. So we need to clarify, because a student can do this. I say, okay, I want Q1 to be the first bit and Q0 to be the second bit, and this is fine. This is perfectly fine. as long as you continue your design with this. But usually we don't do this. I mean, Q0 is for first bit, Q1 is for second bit, and so on. There is no need to mix things and to to reverse things, because otherwise you need to take it into consideration here. When you put it here, you need to put Q1, Q0, and then you need to take care of the which one, D0, which one, D1, and so on. So there is no need to complicate your life. We always say, okay, the first bit or the first flip-flop will give us the first bit, second flip-flop will give us the second bit, and so on. And then we go to the excitation table. I mean, usually we do, I mean, if we follow the steps that I explained previously in the previous lecture, the next step should be the state diagram. But because this is simple, I mean, we don't have any extra inputs, so we know that, of course, I can draw it here, the state diagram. There's no problem, so we can add it here. So 0, 0 is the first state. Then we go to 0, 1. Then we go to 1, 0. Then we go to 1, 1. So this is the sequence. And then we go to, so every clock cycle, if I am in 0, 0, and then there is the next rising edge of the clock cycle, we go to 0, 1. And then if I am in 0, 1, I go to 1, 0. There are no conditions here. I have no extra inputs, so no conditions. The transition will happen every clock cycle. And then I will use this for the excitation table. Now, remember we have Q0 and Q1, so I need to include them both. And then I added an extra column here. This will help me. So if we say the current state is 0, which means it's 0, 0. So Q0 is 0, Q1 is 0. If we are in state 1, so those are the, I'm listing here the possible states. We have 0, we have 1, we have 2, we have 3, and this is the binary, right, for them. Now, remember the excitation table, what we need to do is to find out what is D0 and D1 in our case. So if the current state is 0, we are here. What should be the next state? I added an extra column here to show the next state. The next state should be 1, right? So first state is 0, next state should be 1. How do I get 1? What is 1? 1, it means I need to get, we'll use red here. I'll use a different color, green. I need to get 0, 1, right? For Q0 and Q1. So Q0 should be 1 and Q0 should be 1 and Q1 should be 0 for next state. Now, if the current state is 1, what should be the next state? The next state should be 2. So which means I need to have this. I will do this for all possible states. Now, if it's 2, the next state should be 3. If it is 3, the next state should be 0. It goes back to 0, right? Using the flip-flops, it's easy because the next Q, how to get the next Q? By just putting on D what I want as next Q, because Q is equal to D. And that's it. So now, if I want 0, 1 as next state, then I need to put 0, 1 here. If I want 1, 0, then I need to do 1, 0 here. If I want 1, 1, then I need to do 1, 1. And if I want 0, 0, I just need to do 0, 0 here. And that's it. The flip-flop, I think, is very simple. Is this clear? How did I get the excitation table, right? I don't have any extra input in my circuit. So it's just a counter. I have clock. And then I have output, which is 2 bits. That's it. Inside here, we have 2 flip-flops. So I know that I have 2 flip-flops, and I know that this clock will go to both of them. This is what we are doing. We are doing a synchronous counter. So the clock will go to both of them. It's the same clock. We are doing this because it is a synchronous counter. If it was asynchronous, I don't need to do this. I know the circuit in advance. Is this clear? or no?
Yes, Doctor. So.
Okay, good. So, and then next step is to find out what is D0 as a function of Q0, Q1, and I need to find what is D1 as a function of Q0, Q1. Those are the next steps. And then once I get the expression for D0 and D1, I will just draw the circuit. From this truth table, of course, I'm not going to repeat those again, how to get them. So we will get D0 is equal Q0 bar. So D0 is basically Q0 bar. I don't need anything else. I don't need any circuit, any components. I will just take Q0 bar and connect it to D0. D1 is equal to Q1 XOR Q0. And that's it. So we'll just draw the circuit now. I have my circuit. So what do we need? We need an XOR gate, and we need the 2 flip-flops, right? The clock for both of them is the same. We are doing a synchronous counter. The clock is the same. And then we said D0 is equal to Q0 bar. And then we said D1 is equal Q0 XOR Q1. And that says this is my circuit. Of course, I didn't represent here the final outputs. I need to take, this is Q1, and I need to take Q0. So this Q0 and Q1 will give me my final output. Oh, sorry, this is 2 bits. This is my final output. So Q0 is the first bit, Q1 is the last bit. And this is a synchronous, it's 2-bit synchronous counter. So it counts 0, 0, 0, 1, 1, 0, 1, 1, and then back. That's what it keeps doing. So which is similar to the other one that we did where the clock goes from the asynchronous. So you see for synchronous, we need an extra gate, XOR gate, to be able to do the counting because it's synchronous. The counter, the clock is connected to, or both flip-flop, they have the same clock. Of course, I can replace this gate with a multiplexer using the 1-level or 2-level implementation if I want. So in this case, and you know how to do it, right? So I will just use this table to get the D0 and D1. So this is the multiplexer. This will be the connected to Q0 bar. So there is no need for multiplexer. D1, I can use this multiplexer to replace the XOR gate. And that's it. You know how to do it, yeah? So this is from the truth table. And this gets to the multiplexer. Of course, Q0 and Q1 will be the control lines. This is 1-level implementation. I can do a 2-level implementation if I want, right? So how can we get the 2-level implementation for this one? So we have D1. Sorry, I will put Q0, Q1, Q0. And then we have D1, 0, 0, 0, 1, 1, 0, 1, 1. And we get 0, 1, 1, 0, right? From what in the previous slides, right? So how do we get the 2-level implementation?
You break it into rows.
Yes, go ahead.
You break it into 2 rows and you find it as a function of DQ0.
Yes, excellent. So this is basically what we did, right? So all of you should know how to get this. So we just, as you said, we split it into rows. And now we try to find D0, D1 as a function of Q0. So 0, 1, 0, 0, then this is Q0, right? And then 1, 0, this is what? Q0 bar, right? The good thing, we have already Q0 bar. We can just take it with any inverter. And this is why it's good always to have Q0 bar. So I can then replace this one, this here. I don't need, what do I need to have it to have? I need to have a, let's put this here, a 2-to-1 multiplexer. So it will have one control line. The control line will come from where? This control line,
Q0.
and then we have two. It's Q0. Q1, not Q0, no?
Q1, yeah. The outputs are Q0 and not Q0.
So this will be controlled by Q1. The inputs are now, the inputs for this multiplexer are Q0 and Q1. And the output is D1. And then this is D1, the outputs. This is the output. And we have the two lines. We said one is Q0. So I can just take Q0 from here. And the other one is Q0 bar, which I can take from here. 2-to-1 multiplexer. So I can do whatever I want. I can use gates or I can use multiplexers. So, and you know how to get 1-level and 2-level implementation. Right. I hope the concept is clear. Now we will do another example. I want to do a reversible 2-bit synchronous counter. So what does it mean? So it's a counter. Again, I want 2 bits. This is 2, this is O. So we will have clock and the clock. So 2 bits, this means I need 2 flip-flops. And this means this clock will go to both of them because we say it's synchronous counter. And then this counter has an extra input, which we call UD. Reversible, this means this counter can count up or count down. So if UD is 0, or if UD is 1, this counter will count up. It gives us 0, 1, 2, 3, and then back normal counter that counts up. If this UD is 0, this counter will count down. So if it is 0 now, we will go to the previous state, which is we count down 3. And if it's 3, it goes to 2. And if it's 2, it goes to 1. And if it's 1, it goes to 0. And then keeps doing this. So now this is the state diagram for that counter. So I think the states are clear. I have 4 states. I have 0, 0. I have 0, 1. I have 1, 0. And I have 1, 1. Now we are not just counting up. We have an extra input, which we should include in our design process. So it's called UD, and I need to consider it. Now, if I am in this state, and UD is 1, the next state will be 0, 1. So this is the condition here. Now, if I am in this state, and UD is 1, then I go to the next state, which is 1, 0. If I am in this state, and UD is 1, I go to 1, 1. If I am in 1, 1, and the UD is 1, I go back to 0, 0, and so on. Now, if I am in here, and UD is 0, then I need to go back to 2. So this is the next state. So each state, as you can see here, has 2 possible next states. 1 could be the next state, which is we count up, or the other one we count down, depending on UD. This is the state diagram. Is this clear? And this is very good example that shows a condition, a full state diagram with condition. Is this clear?
Yes.
Next step. Okay, good. Next step is to get the excitation table. Here, in addition, remember we have 2 flip-flops. So we will have Q0 and Q1. We will have D0 and D1. And then we will have an extra input, which is UD. I need to consider it in my design, in my excitation table. And those are, so basically those are like my 3 inputs, Q0, Q1, and UD. And those are the possible cases, right? If I have 3 inputs. This is like a normal truth table. So I have 8 possible cases. As you can see, when UD is 0, this means we are counting down. If UD is 1, for this 4 cases, when UD is 1, we are counting up. I added those 2 red columns to help you to understand. You don't have to put them, because now you can just use the state diagram. So basically, I got those from the state diagram. What does this mean? It means if the current state is 0, this is 0, right? 1, 0, 0. This is 0. 0, 1 is state 1. 1, 1, 0, 1, sorry, state 2, and 1, 1 is state 3. Now, if we are in state 0 and UD is 0, next state should be, we are counting down. Next state should be 3. If we are in state 1 and UD is 0, counting down, next state should be 0. If we are in 2, counting down, next state should be 1. If we are in 3, counting down, next state should be 2. And that's it. Working again with the flip-flop is very simple. We just look into the state that we want next, and this will be the value of D0 and D1. If I want 3, this means I want 1, 1. If I want 0, this means I want 0, 0. How do I get 1, 1 in the D flip-flop? By just putting 1 on each D, and then I will get 1, 1. And then I will complete the table. I will go to the next 4 states. So again, if we are in 0, this is 0, 0. This means it's state 0. If we are in state 0 and UD is 1, I go to state 1. And I will complete all possible cases. Is this clear? And this is the full excitation table for this reversible 2-bit synchronous counter. Next step is to get D0 and D1. So now we will get D0 as a function of U0, Q1, and UD, because we have UD here. D1 is a function of Q0, Q1, and UD. This is what I need to get next. And of course, you can use the K-map, and you can, use Boolean algebra to reduce it further. So the K-map will not give me this, so I reduced it further, which gives me D1 is equal UD XOR Q1 XOR Q0, and D0 is basically Q0 bar. I just connect Q0 bar to it, and that's it. So next step is to draw the circuit. How many flip-flops we have? 2. So the first thing is to have the 2 flip-flops. We connect I need 2 XOR gates. Sorry, this is XOR, and this is XNOR. So this is, I need to do Q0 XOR Q1 first, and then I do UD XNOR the result of this. So I have 1 XOR gate and 1 XNOR. And then D0 is Q0 bar. I just connect it to Q0 bar. And then I will connect the rest according to this expression, D1. And then we have our UD, and that's it. So this circuit, of course, I can take now Q0 from here, and then I will take Q1 from here to give me the final output. I didn't put it here in this diagram, but I think you should know this. So this is output, which includes Q0, Q1. Now, and you can try this, you can play with waveforms. You can even design this in VHDL and you can simulate it, and you should get, if you have 0, 0, and you put UD 0, the next state will be 3, 1, 1. If you are 0, 0, and you put UD is 1, the next state should be 0, 1. You go to 1, increment. Here decrement, here increment. Is this clear? Good. Now I'm going to move to modulo and counters. And what I put in bold here is the difference between a modulo and counter and the normal counter. So modulo n counter has only n valid states and doesn't necessarily perform a binary counting sequence. So I can have a 3-bit counters that does this 0 0 1 0, counts up by increments by 2. And then what is next? Sorry, say 3 bits. And then next is this one, 4. And then next is 6. And then, so I have 3 bits, but I'm not using all states. With 3 bits, I can have up to 2 power 3 minus 1. I can go up to 7. So I can have 0, 1, 2, 3, 4, 5, 6, 7. I'm not using all states here. What does this mean? It means that state 0, state 2, state 4, and state 6 are valid states. The rest are invalid states. I don't need them. And I call this a modulo 4 counter. It has 4 valid states. And one very important point here is when you design this type of counters, you will need to consider the invalid states. In case the counter will go to an invalid state, you should redirect it to one of the valid states, and then the counter will start working again. If something happens to your circuit, and for some reason the counter is not supposed to give you an invalid state, but for some reasons it gives you an invalid state. Something happens to the circuit, and then you will get state 3, which you don't need. You should consider this in your design, so you can redirect this 3 to one of those states, and then the counter will start again. It's like you are initializing the counter again to start from a valid state. And this is very important. And of course, the number of flip-flops, the design approach is almost the same as what we did before, in addition to including all the states, even the invalid states. And then the main difference is the number of the way how to find the number of flip-flops. Because sometimes you may not need to have, you may be able to use 2 instead of 3 flip-flops, and so on. But for example here, and again, one clear way to find the number of flip-flops is just to look for what is the highest possible state that you need. The highest possible state is, for our case here, for example, is 6. How many bits I need to represent 6? I need 3, so I need 3 flip-flops. That's it. So you always look for the highest state. What is the value of the highest state? How many bits do you need to represent this highest state? And this will be the number of flip-flops. So this is one simple way to do it. Or you can use this one. Modulo n counter has n states, where n is defined by n is less or equal to power m. And then you use this, you look for you round up. You may get a real number here, a real number, so you round it up to the nearest one, of course, and then m will be the rounded value, the nearest integer value. Let's give you an example here. So we want a counter that does this sequence 0 1 2 0 1 2. So it counts from 0 1 2 and then goes back. So which means I don't need 3. I stop at 2. Remember, when we talk about modulo n, we are not talking about asynchronous. I cannot do it with asynchronous. Asynchronous is a counter that counts up, and that's it. Now we need different sequences, so automatically it's synchronous. Right. So if I follow this, I have 3 states. 0 1 2, 3 states. So n is equal 3. So m should be more or equal logarithm 3 divided by logarithm period 2, which gives me 1.58. So when we round up, the nearest one is 2. So I need 2 flip-flops. Or in a very simple way, what is the highest state? Highest state is 2. What is 2 in binary? Is 0, 1. This is the minimum number of bits that I need to represent the 2. I need 2 bits, so 2 flip-flops. Both answers are correct. Use whatever you think is simple for you when you design, or when you have something like that in a question. Then I'm going to use Q0 for the first bit, the least significant bit, and Q1 for the most significant bit. And then I'm going to design my circuit, or to get the excitation table. Again, so I'll have state 0, state 1, state 2. Those are valid states. I call them here valid. And then I added state 3. I don't need state 3, but I need to consider it in my excitation table. 3. It's invalid. Right? And then if I am in 0, I need to go to 1. If I am in 1, I need to go to 2. If I am in 2, I need to go to 0, not to 3, right? This is what I want to do. Go from 0 to 2. 0, 1, 2, 0, 1, 2. That's what I need to do. So, and now if I am in 3, which is unlikely to happen, but if it happens, I need to redirect it to one of those states. Which state should I choose? Is the state that will give me the best logic. So I can basically, ideally, here I put state 2. But ideally, it should put XX here. And of course, those XX should not be both of them equal to 1, 1 at the same time. I mean, they should not be equal 1, 1. Because if I put 1, 1, this means I will be redirecting my state to state 3. And this is wrong. I don't redirect an invalid state to another invalid state. So there is a condition here. So I put XX, where this XX could be 0, 0, it could be 0, 1, it could be 1, 1, 0, one of those states. So those are fine, but I cannot have 1, 1. So I put XX initially, and then I can do the K-map, and then I will replace those X's with the best value that, or the value that will give me the best logic. I did this myself, and the best one were those values. So this D1 is equal Q0, so it doesn't give me any, I don't need any extra gates. So I end up having 0, 1, which means I will redirect this to state 2. Is this clear? And then D0, I found out that D0 is 0. Of course, you can put 0 here if you want, and this is good as well. 0, 0. If you do 0, 0, you will get Q0 bar and Q1. So this is fine as well. As long as you are not using 2 gates, so it's one simple gate. So I got those, then I just draw my circuit. So I use the NOR gate, just simple one NOR gate, and then to get my circuit. If you test this circuit, of course, you can add here the final output, Q0, and you take Q1 from here. Those will give me the final output, which is out. If you use the circuit, you should never get 3, 1, 1 up here. In a normal working scenario, you will never get 1, 1. In case you get 1, 1, let's say that I have a preset here. This is preset, this is preset. I will do preset for both of them. So preset is connected to this. I will do here preset. I will get 1, 1. Then the next state will be 2. It will branch to 2. and then it will start the sequence, the normal sequence. I hope this is clear. Yes or no? And it's not. Do you have questions? Please feel free to ask. Right. Let's do another example. So I want to design a 3-bit gray counter, code counter. So this is a counter that doesn't follow the normal sequence. So it's considered as a modulo and counter, but I can have all possible cases. So it's not necessary I will have just few cases. So all cases are valid. So we say 3-bit, which means I will need with 3-bit, we need 3 flip-flops. What is a 3-bit gray code counter? You know the gray code, right? Remember. So we say when we do the K-map. So you are allowed when we go from one state to another. So if I have 0, 0, when I go to the next state, I'm allowed to change 1 bit only. I can do 1, 0, 0. So this is a possible next state. And then I can do next one, it could be 1, 1, 0. So I'm changing only this one, the middle one. I'm not changing the first. And then I can, by doing this, so this is the gray code. Yeah, when we go from one state to the next one, we are allowed to change only one of the bits. By doing this, I can have multiple sequences, right? So I can have, for example, 0, 1, 3, 7, 5, 4, 6, 2, and then back. So I'm using a gray code counter. It's not a normal counter, and we are using all the possible cases. I can have this sequence, for example, 0, 1, 3, then 2, 6, 7, 5, 4. All of these are valid sequences, and they are correct. There are more. These are not the only 3. You can find more sequences where you meet the condition of changing only 1 bit at a time when you go from one state to the next one. So let's choose the middle sequence. So I'm going to do this one. For example, if I have this sequence and I want to design this circuit that will give me this counting 0, 1, 3, 2, 6, 7, 5, 4, and back 0, 1, 2, 0, 1, 3, 2, 6, 7, 5, 4, and so on. So I will use Q0 as the most significant one, Q1 is the middle one, and Q2 is the Q0 is the least significant one. This is the first bit. Q1 is the middle one, and Q2 is the last bit. So we need 3 flip-flops. Remember, so this is the sequence that we want to do. This counter doesn't have any other inputs. It just has the clock, and that's it. It doesn't have any other inputs. So we have Q0, Q1, Q3. And those are the possible states. 0, 1, 2, 3, 4, 5, 6, 7. And here in this example, we don't have any invalid state. They are all valid. Now, next, we go from 0. If we are in 0, what is the next state according to this one? Next state should be 1. If we are in 1, what is the next state? Next state is 3. If we are in 2, what is the next state? The next state is 6. If we are in 3, what is the next state? The next state is 2. So I'm just following this one here. Of course, you can do the state diagram, right? But because it's simple, it doesn't have any conditions, there is no other inputs, it's clear. The transition between the states is simple, it's very clear. So there is no need to draw the state diagram, but you can do it if you want. And then that's it. And then we just do 1. How do we get 1? By doing 1, 0, 0. How do we get 3? By doing 1, 1, 0. How do we get 6? By doing 0, 1, 1. All the examples that we did here, we did them with D flip-flop, and which is simpler than the other one. But we will do more examples later on in the tutorial with JK flip-flop. We can try the other one. We can do it as at the end of the session. This example here. So we can try to do it with JK. Right. Is this clear? And then now all what I need to do is to find what is D0 as a function of Q0, Q1, Q2. And do the same for D1 and do the same for D2. Of course, you can use K-map, and then, or sometimes K-map doesn't give you the, doesn't help, so it doesn't give you the best one. I mean, it cannot be simplified. You can rearrange things to get it into XOR gate, or so. This is my circuit, and then I have multiple gates here, and this will give me the sequence that I want. So it's not a normal counter; it gives a different sequence, and of course I can take now Q0 from here. I can take, this is Q1, and then I can take Q3, this is Q2, I can take it from here, and this is the output. 3-bit, this one is 3-bit. And this will give me the sequence that I want here. So basically you can do whatever you want, whatever sequence you want. Of course, the circuit can get complicated when you, I think one simple solution to this is to use multiplexers here. I think this is easily done if you use 2-level MUX. And this will simplify your circuit further. You can use a ROM if you want as well. It depends on the complexity, but it's not too complicated. You can get this to just use NAND gates. You can do whatever you want with what we did before. And that's it. This is the last slide and the last lecture in this course. Let's do this example, as I told you, with the JK, since we still have some time. Well, let's do this one to avoid the valid states and invalid states. So just to avoid the, because we will do them as well in the tutorial. This one, a counter that counts up. We want to do it with JK, 2-bit counter. Synchronous. So it's clear what we want, yeah? So we want to do a, let's switch to the, so I want a 2-bit counter. So we'll start with, so 0, 0. We go next to 0, 1. We go next to 1, 0. And then next to 1, 1. And then back to, so this is a simple counter. There are no conditions, no other inputs. So I need to put Q0, Q1, 0, 0, 0, 1, 1, 0, 1, 1. And now I'm going to do the excitation table. What should be the next state? Next Q.
1.
Or I can put, to be more precise, Q. This is Qn plus 1. I want it for 0, Q0, and Qn. Sorry, I put 1 here. Qn plus 1. I want it for, sorry, Q0 and Q1. This is next state. This is current state. Right? 0, 0. So if we are in current state 0, 0, what should we get next? We should
0, 1.
get 0, 1. If we are in 0, 1, what should be next? Should be 1, 0. If we are in 1, 0, what should be next? 1, 1. If we are in 1, 1, what should be next? 0, 0. So far, I'm just putting this state diagram I'm just mapping it into this excitation table. I didn't do anything extra. So if the current state is 0, 0, I should get 0, 1. If the current state is 0, 1, I should get 1, 0, and so on. Now, the most important point is remember, if we use JK, we will have J0, K0, right? And we will have J1, K1. So here we will have 4. J0, K0, and then we will have J1, K1. Right?
So we're mapping J0, K0 to Q1. In this case, we're mapping Q1 to J0, K0, yeah?
Q1, no, Q0. It doesn't matter. I mean, just the order. It's fine. Yes, you can change it. We are not mapping, but I mean J0. When I say J0, it means it's related to Q0. Yeah. It doesn't matter how I put them.
Yeah. Okay.
It doesn't matter. Yeah. So you can do this if this will avoid confusion. So this is for Q0. This is for Q1. Yeah. We have two flip-flops. J0, K0, Q0. And we have J1, K1, Q1. Of course, and then Q1 bar, and then the clock. So those are the flip-flops. I need to find what is now. I'm looking for J0 as a function of Q0 and Q1. And then what is J1? Same. And what is K0? Same. And what is K1? Same. This is what we did, right? For the D flip-flop as well. Now I will start with the first flip-flop. I will start with the first flip-flop, J0. I'm going to put the excitation table here for JK, so for you to remember. Qn plus 1, 0, 0, 0, 1, 1, 0, 1, 1. And then we have J and K. And this is what we have, 0x, 1x, x1, and then x0. Right? So now I will start with Q0. First state here. Q0 is 0. What do we need next for Q0? What should be what?
1.
The next state should be 1 here. I'm working with Q0. I'm starting with the first flip-flop. Q0 is 0. We will get Q0 from the first flip-flop, and we will get Q1 from the second flip-flop. So I'm starting with the first flip-flop, Q0. If Q0 is 1 for the first state, the next Q0 should be 1. Yeah, this is what we got from the state diagram. Next state, if Q0 is 1, the next state should be 0, and so on. Now I will start with the first one. Back to the first one. Q0 is 0. I want it next to be 1. So what should I do on J0 and K0? Get 1. Huh?
1 and X.
1 and X. I'm just following here. We are here. I'm 0 and I want next 1. So it's 1X. Next. Current state is 1. I want next one to be 0.
X.
X1. Excellent. Next, it's 0, and I want the next one to be 1. So it's similar to the first case. It's 1x, right? And then 1. Next current state is 1, and I want the next one to be 0.
X.
1, 0. It's x1. And that's it. I'm done with the first one. I'm going now to move to Q1. And you need to repeat this if you have 3 flip-flops, 4 flip-flops. You need to do the same for every flip-flop. Now, Q1 is 0. Let's try to use a different color. Q1 is 0. I want the next one to be 0. So 0, 0, which means in J and 1, I need to do 0x, right? According to this table here, 0, 0. 0, 1, I need to do 1x. 1, 0, I need to do x1. 1, 1, I need to do x0. And that's it. Is this clear?
Yes.
Now I'm done with the excitation table. This is all what I need to do. And this is the most important part. What I need to do now is to replace those x's with what I want. That will give me the best logic. And you can see it from the table. What should be the best logic for K0? What is the best logic for? Huh?
We can put x as 0, so it would be q0.
You put x as 0, so it should be q0. So if you do 0, 0 here, I will get K0 is equal, oh sorry, K0 is equal Q0, 0, 1, 0, 1. It's equal to Q0. Or I can put them both 1, which gives me K0 is equal 1. You just connect it to VCC. But both are correct, are good. So I can do K0 is equal Q0. Next one, K1. Oh, sorry, J0 is equal what?
You can also put 1, 1 and make it equal to 1, or 0, 0 and make it equal to q0 bar.
Excellent. So I can do Q0 bar. Or if I put them 1, 1, I can do, sorry, J0 is equal 1. And both are good, because I'm not going to add any extra logic. Thank you. Next. For K1.
1, 0, so it would be q0 bar.
1, 0, I will get Q0 bar. This is K1. Excellent. So if I put 1, 0 here, it will give me Q0 bar. Next.
And 0, 1 and it would be q0.
If I do 0, 1, it will give me J1. And do you see, it's always the case when you work with JK flip-flops, it is harder to design. I mean, you have more time here, but the logic will be simpler because you will be able to get to just to use, you know, Q0, Q0 bar, and the just put 1 or 0 in the J and K. There is no need for any extra gate. So you said it's equal to Q0, and that's it. We are done. Last step is to draw the circuit. So what do we need for the circuit? I need 2 JK flip-flops, J0, K0, Q0, Q0 bar, J1, K1, Q1, Q1 bar, right? And then clock is the same clock. It's synchronous, so it's same clock for both of them. And then I have JK. What do we do? I'm going to use different color for the connection. We say J0 is equal, or K0, sorry, is equal to Q0. That's it. Oh, sorry,
K0, actually, that not
K0.
not.
Yeah, so K0. And then Q0 bar is equal to J0. And then K1 is equal to Q0 bar. So I can get it from here, K1. And then
Q0, not Q1.
Oh, sorry, it's Q0, yes. So again, I need to use this same Q0. Q0 bar. It's very easy from here. And then J1 is equal to Q0. And then that's it. Q1, the final output is this one, Q1 and Q0. This is my final output. 2 bits. You see, with JK flip-flops, the circuit is simpler. We don't need any extra gates, just wires. And this gives me a counter. Okay, I think that's it for today. I think we did many examples. We showed you how to use JK flip-flops. So we will do more in the tutorial, inshallah, which will be next session. And then that's it. We will finish. So it's good that we managed to finish all topics on time. The time that we have left, it will be for. I already sent an email for the or announced on Blackboard for the next quiz. So the next quizzes we will do both of them during the normal lecture session. So there is no need to have
so
do
there's
them
no quiz
outside.
tomorrow, doctor, right?
Pardon?
So there's no quiz tomorrow.
I didn't say we will have quiz this week. So we said it's this week. We said it's for the homework, and I said the next quiz we will have it next. I mean the quiz 3 we will have it the week after, which is next week. So this is what I mentioned last week. So we will have it. I already announced it, so it will be next week on Tuesday for you. So you have 1 week, and it will be on 2 topics, which is the others and the latches and flip-flops. And so this one is not included. This will be for the final one. It will be pure multiple choice questions. And this time, the next quiz, it will be pure multiple choice questions. Now for the report, I talked to the TI. I got groups from one of them, Engineer Hamid. I told him that we can go for groups up to 4. Even if you didn't do the work in the lab together, you can always submit the report so. For example, let's say that we have 2 groups, groups of 2 students. They did the labs independently. I mean together. I mean 2. So 2 students, they work together. You can merge when you submit the report. It's fine. You can have a group of 4 and submit a report. It's up to you. We can have up to 4 students. Those who didn't, who are not doing the lab, they should, as soon as possible, join one of the groups. The assessment, I'm going to repeat this. The assessment for the theory is for the report. And there are many things where a student can contribute in the report. And you need to show this. I mean, there is in the last page, you need to show a contribution page for the name of each student, and he contributed to which section. So you need to insert this at the end. If it's not already in the template, I will add it. I will make it clear. We need to show we need to see contribution. Someone who hasn't contributed will get 0. If you are not doing the lab, you can contribute to all aspects. I mean, because it's pure simulation, you can even at least, contribute to the design of the multiplier that we gave you. So this is like it's pure theory, so you can work on this. And you need to let me know as soon as possible the names of your group mates. So if you are not doing the lab, I will expect an email from you with the names of the students in the group that you are going to join. Is this clear? Do you have questions about the report? I already put the submission requirements, what we expect from students to add in the report. If you have questions, please feel free to send them by email or just send me or request an office hour. Is this clear? So this is, remember, we will be assessing the report. Even if you cannot complete the work and you write a good report, you can get a good grade. We are assessing the writing skills, the presentation of the work, drawings, everything, English. So this is the aim. For in the lab, the technical work, you will be assessed about it in the lab. You will show your result, you will show everything. But here you are reporting, you are showing for someone who hasn't been with you in the lab and didn't see your work, explain to him what have you done in a good and professional way, in professional manner. Because this is what you will do later. In your SDP, you are not going, your external examiner will not be with you. It's not like your supervisor, he knows exactly what you have done. So you need to write a good report for him to explain what you have done. And this is the aim of this task, of this assessment in the theory part of of digital systems. I also put a template for you to use. So all students, they should use the same template. And this is what you will do as well when it comes to your final SDPs in your design project. There will be one template for all of you to use, and you need to follow the template. And this is what you will do for those who will continue in research or whatever. If you want to publish, you will have to always to use a template from the publisher. And you need to follow it. So make sure. So do you understand what I mean here? The task here, what we are aiming, is not just the technical thing or the technical skills. There are other soft skills that we need to see. And this to prepare you for the coming activities, including your senior design project. Right. Again, if you have any question, please feel free to send me an email or just request an office hour, and I can answer your questions. That's it for today. We have, as I said, we have one tutorial left. So next quiz, quiz 3 will be next week, and then we will do the last one the last week, the last session of last week, which will be the last Tuesday. We will do a revision if we have time, or otherwise we will have a I will always post questions, revision questions, plus the answers to the questions for the revision. And I always do this as well. I always offer extra office hours. So I will send you the timings to help you with your revision, with your preparation. So we'll set depending on the time, of course, 2 to 3 extra office hours, where you can come and answer any question that you might have during the revision session, the revision week. Or I think the good thing for your case, you will have your exam not the first week, so you'll have some time where we can have at least 3 extra office hours to help you with your review. That's it from today. Do you have questions? If you don't have questions, then we'll talk to you next session, inshallah.
Thank you, Doctor.
Yes, no problem. Yes.
Doctor, so do you mean the students who take the lab previously will be assessed only on report only?
Yes, it's the report only. Yes, you will submit the report. What I will see from you is the report.
Oh, okay, but not individually, right?
Not individually. You need to join a group.
Okay, thank you, Doctor.
Yeah, no problem. Okay, so any question? Any other questions? If not, then talk to you next session, inshallah. Assalamu alaikum.